Hello and welcome, class, to part 2 of chapter 18, where we are going to be wrapping up our conversation for solubility, at least in terms of reversible reactions. So we spent a great deal of our previous lecture just talking about solubility quantitatively, how we can determine whether or not a precipitate is going to form or whether or not a solid is going to dissolve, and to what degree. In this section, we are going to be talking about how we can manipulate that solubility using Le Chatelier's principle. So let's tie Le Chatelier in with this concept of solubility, because if we have some type of solid that's reacting reversibly to make some hypothetical cation and anion, well, surely then, since this is a reversible reaction, Le Chatelier's principle is going to apply. So if we create some type of stress and apply that to the reaction, we're going to be able to shift it either to the right or to the left. And we can predict the shift in the exact same way that we did in chapter 15 when we looked at Le Chatelier's principle. So solubility of these mostly insoluble compounds are going to be affected by a number of factors, and these are the 4 that we're going to focus on. The common ion effect, which is a new term that we're going to introduce in a couple of seconds. We have temperature dependence, just like before. In chapter 15, temperature, we said when we were taking a closer look, didn't just shift the equilibrium, but it actually changed the value of K itself. So the same concept is going to happen here, since the dissolutions of these types of solids are going to be exothermic or endothermic. Most of the time they're endothermic. We would be able to predict some type of temperature response to solubility of these reversible reactions. Acidity and alkalinity, as long as you know what an acid and a base is, that's the total amount of information that we need to be able to have this conversation. So we're not going to be tying in any type of like weak acid base pH type of calculation here. It's just a simple, if you add acid or base, you can predict a shift in the reaction's solubility. Last but not least, complex ion formation. So we already know what a complex ion is. We've talked about this in lab a couple of times. These are the types of ions that are not just simple form, but they're polyatomic ions, normally containing some type of metal in the center. They're surrounded by some number of what we call ligand. In this case, I'm just drawing a bunch of ammonias, NH3s, surrounding this copper, and the total complex, where each of these bonds is not a covalent bond, it is some type of non-covalent or dative bond. It's an intermolecular force holding each of the ammonias to the copper, and this whole thing is going to have a polyatomic ion charge of +2. So this is what we mean by a complex ion. And complex ions can form in solution, and that's going to also affect the solubility of your mostly insoluble compounds. Okay, so let's talk about how each of these then variables in turn affects solubility, starting with the common ion effect. Okay, so what the common ion effect is, first we have to break down what is a common ion before we can talk about the effect it has on your solution. So a common ion is this first definition. It is a solution that is already going to contain some type of solute ion that is in common with your reversible reaction. In other words, if we wanted to add magnesium carbonate into a solution, not a pure water bath, but a solution of magnesium 2+. Let's say there's just a bunch of magnesium 2+ already floating around in the solution, and we add magnesium chloride to it. The magnesium 2+ that's already present in solution is going to be the common ion. Since when magnesium carbonate breaks up, one of the species it breaks into is magnesium 2+. Here we can see the magnesium 2+, which is already present, is an ion that the 2 pieces have in common. One piece being the solid that you're going to add into solution, your magnesium carbonate. The other piece is the ion that's already in solution. All right, so the effect that this common ion is going to have is that it decreases the solubility of your mostly insoluble compound. Now, we would be able to predict this already according to Le Chatelier's principle, right? If you increase the concentration of one of your species, if you increase the concentration of your magnesium component, your magnesium ion in this case, we would predict that we are going to get a shift away from the ideal equilibrium because we've increased the concentration of one of our products artificially, And so what we're going to do, again, here's our little Hot Wheels car. This car is going to represent the shift in the reaction according to Le Chatelier's principle. If we increase the magnesium 2+ concentration, we predict that this reaction is going to shift back towards the magnesium carbonate in order to reaccommodate and reach equilibrium. Now, this exactly demonstrates what we just said. A common ion, in this case the magnesium 2+, is going to decrease the solubility, and the solubility decreases because the reaction shifts back towards creating more of this insoluble solid. Okay, so if we want to, though, put some quantifiable calculation to this, can we do that? Can we predict, well, what is the new solubility if we already have some magnesium present? And the answer there is, of course we can. We can always quantify. The question is, do we want to? And here the answer is yes. So before, the solubility that we found for magnesium carbonate was a 0.22 grams per liter, right? That was like 2 or so examples ago. So what we're going to do now is take the same magnesium carbonate and we're going to add it to a 1 molar solution of carbonate, right? We just have carbonate solution, like soda or baking soda. Let's say we just added a bunch of like sodium carbonate. Sodium doesn't matter. The carbonate is the common ion. So what is the new solubility of the magnesium carbonate in solution in grams per liter? Right, so before, the magnesium carbonate in just pure water, its solubility was 0.22 grams per liter. So we're going to kind of keep this in the back of our mind. How we set up this calculation, we are going to be using the ice table type of format again. So let's set up our reversible reaction. The magnesium carbonate, which is a solid, is going to dissociate and create magnesium 2+ in aqueous solution, and the carbonate 2- also in aqueous solution. So the major difference here when setting up our ice table, because before we didn't have any magnesium or carbonate initially, we just put 2 zeros here with our initial conditions. The only real difference is that now we have some type of additional piece. We have 1 molar solution of carbonate initially. So this 1 molar solution of carbonate is going to have to go right here in the initial condition under carbonate. Now we don't have any magnesium. That part is still consistent. We don't have any common ion of magnesium here, but we do know that since there is a 0 here, we are going to get some type of shift from reactant to product in order to create some magnesium. And again, the amount of the magnesium carbonate specifically doesn't matter. Since we're working with a solid, we're just going to put dashes all the way down the line. We don't have to worry about what this reactant concentration is, since there's no concentration of solid that we can actually measure as a variable. So the shift that we're going to get is going to be from left to right. The change that we're going to predict is that we're going to create at least some magnesium here. We're also going to get a +S here, since both of these are on the product side. We're going to get a shift from reactant to product, creating a little bit of both of these. So the equilibrium concentration of our magnesium is going to be an S, and the magnesium carbonate concentration at equilibrium is going to be a 1 + S. Okay, so here now we have a way to calculate what the S is going to be using our equilibrium expression, right? Our solubility product for this species, which was given before, is a 6.8 × 10⁻⁶. This value is still the same. The 6.8 × 10⁻⁶ value is going to be equal to, again, our concentration of magnesium 2+ times our concentration of CO3 2-. This does not change. What does change are the variables that we're going to be plugging in for the magnesium and the carbonate. The magnesium is a value of S. We don't know what this unknown change is. That's going to be exactly what we're solving for. The concentration of our carbonate is a 1 + S. So here we now have a setup, an expression where we have one equation and one unknown. This is our S. So let's distribute our S into the parentheses here. We have an S + S squared. And all of this is going to be equal to the equilibrium constant value, this equilibrium constant of 6.8 × 10⁻⁶. So we're going to subtract this to the other side. We're going to subtract it, because currently it's sitting right here. We're going to subtract it over 6.8 subtract it, times 10 to the negative 6. And this gives us a way to use the quadratic formula, to solve for what our S is going to be equal to. Now, I'm not going to show all of that work. I leave that algebraically as practice for you. But when going through the quadratic formula and solving for our new S, given these conditions, what our solubility is in molar units, again, because first we find molar units, is going to be equal to 6.8 times 10 to the negative 6 moles per liter. We see such a small shift, a small solubility when compared to the original case, because we have this extra one here. We're starting with some product already. Now, if we convert this using our molar mass, so we have a solubility we can actually compare to the one on the right that is in the grams per liter, we're going to multiply this by 84.31 grams per every 1 mole, since this is the molar mass of the magnesium carbonate. And this is going to be equal to 5.73 times 10 to the negative 4 grams per every liter. Right, so again, this S, I did not explicitly show the math for solving for this 6.8 times 10 to the negative 6 value, but you can use the quadratic formula as we did in chapter 15 to solve for this. Okay, so the value here of the 5.73 times 10 to the negative 4, we can see is definitely less than the value from before when we just added magnesium carbonate into pure water. So this represents the common ion effect, that if you're adding a solid into a solution that already contains some of the product ion, you're going to see less of a dissolution, less of a shift of the magnesium carbonate into the products, since we already have so much of one of the products there. Okay, so just like before, temperature is going to affect your equilibrium expression. Now I'm just going to be focusing on this qualitatively. We've already talked about the quantitative association of temperature and K and all of those values. So what I'm going to do right now is just focus on the heat being as either a reactant or product, depending on if you're working with an exothermic or an endothermic dissolution. Now most dissolutions are endothermic. Most require heat as a reactant in order to break up your compound. The endothermic nature of the reaction then is going to cause temperature to play an effect in the equilibrium balance of the reaction. So let's look at this dissolution below. Potassium nitrate as a solid with a little bit of heat is going to break down into potassium and nitrate ions. This reaction is actually a reaction that we worked with back, it was like lab 11, maybe it was 12, question mark. Where we were measuring the thermodynamic nature of a bunch of stuff, measuring the, in this case it was the enthalpy of solution, and we found that the enthalpy of solution was positive, meaning that we were working with an endothermic reaction. This dissolution of potassium nitrate requires heat. This is also a compound that, according to our solubility rules, is mostly soluble. However, I want to point out that this compound does have a measured solubility. The solubility is 500 grams in a liter of water. And this is at a temperature, greater than room temp. It's around 33 degrees Celsius, not too much higher than room temp, but it is a reasonably high solubility, especially compared to the solubilities that we've just been looking at, right? This is anywhere from 1,000 to 1,000,000 times larger than the solubilities of the insoluble compounds. So that's just to show the range of solubility that we can have here. If a compound is mostly insoluble, we can put a lot of it into any given volume of water. However, this reaction is, again, endothermic. So we would predict that if you were to, let's say, decrease the temperature, what's going to happen is that the reaction, as it is written here with this reversible reaction arrow, is going to shift from the products back towards the reactant. In other words, if you decrease the temperature, you are decreasing the amount of ion that you can actually put into solution, forcing more and more of the potassium nitrate to remain as a solid. even though this is a mostly soluble compound, if we were to decrease the temperature enough, we could turn it into a mostly insoluble compound, right? There is a temperature dependence for this reaction because it is endothermic. And if we were to decrease the temperature so much, this solubility would decrease effectively to a point where it's going to behave as a mostly insoluble compound. Now, if we wanted to look at the flip side of this, let's say the lead iodide, which, as we've been seeing, reacts reversibly to create some lead 2 plus and iodine minus in aqueous conditions, where this is our solid, these are aqueous. This reaction is also, plus heat, endothermic. So we would predict that if we want to increase the solubility of this compound, we would just jack the heat up. If we turn the temperature up, this reaction is going to shift more towards product. We would be able to fit more of the ions in solution. We would turn its solubility up. And in fact, if we increase the temperature of a lead iodide solution to about, 70, 80 degrees Celsius, we can actually get an appreciable amount of the lead iodide to dissolve and turn it into a clear colorless solution and remove all of the solid. All right, so acidity and alkalinity. Again, we're just looking at how acids and bases play with these types of reversible reactions. Okay, so we have a reaction given below. We have iron oxide, which is a mostly insoluble solid, reacting reversibly to dissolve and give us some iron 3 plus and 3 hydroxides. This is a really good example of how an acid and a base can interact with this reaction, since we have hydroxide right here. This is going to be a very straightforward example. So let's say we want to increase the alkalinity of your reaction. We want to increase the alkalinity of the solution. Well, alkalinity is just a fancy word for basicity. It is pertaining to the base component, not the acid. So the alkalinity of the reaction we can increase if we increase the concentration of our hydroxide. So if we add some more hydroxide or add some more base into the solution, well, we can get a prediction that if we're increasing this concentration, we are increasing that side of the track. Thereby, we would predict increasing the amount of solid that we would have in solution, right? The reaction would shift from product to reactant if we added more base into this reaction. Okay, I'm going to switch colors here for this next part. The acid then is also going to have an effect. The acid is going to have an effect because an acid is able to combine with this base. If we add acid into a reaction where OH is present, this will result in a neutralization reaction. Now, this reaction we've talked about back in chapter 9. This shouldn't be anything new. If we add H plus and OH minus, we end up with HOH, which is exactly water. Now, if we add H plus to the solution, what we're actually doing is decreasing the concentration of the OH that is available in solution, since we're neutralizing it and turning it into water. This we would expect then to have a similar effect on the equilibrium, where before we had some nice equilibrium threshold. If we've decreased the concentration of our OH minus, our car then is going to exactly shift in the opposite direction as before. We're going to be shifting from the reactant to the product. So in this particular equilibrium reaction, if we were to add acid to it, we would expect to see more and more of the solid dissolving and turning into this iron oxide dissolved solution. So if there are similar reactions set up with OH minus, H plus being available somewhere in the reaction, changing the acid and base nature, increasing acidity, increasing basicity, or decreasing acidity, decreasing basicity, we would expect to see some type of shift in the equilibrium as a result. And that's specifically, at least in this case, because we see hydroxide is present in the solution. Okay, and the last factor that we're going to talk about, tying Le Chatelier's principle into the solubility product, mostly insoluble type of equilibrium chemistry, is the formation of complex ions. Now, complex ion, again, is that kind of complex polyatomic ion where we have some sort of metallic center to it. So a complex ion being present in solution is known to increase your solubility. So unlike the temperature and the acidity-basicity component, where you can have an increase or a decrease all depending on what the context of your reaction is, here, complex ion formation is always going to increase the solubility of your solid. So let's look at the reaction below to kind of demonstrate why that is. So your solid here, copper hydroxide, is a solid, also insoluble, is able to react reversibly to create some copper 2+ and some hydroxide with a single minus charge in solution. So let's say we want to add some ammonia to this solution. Well, ammonia is known to really, really bond well through intermolecular forces with copper. In fact, if we were to add 4 of these ammonia into solutions, let's just make this a very clear 4. We're adding 4 ammonias to solution. These 4 ammonias are known to surround themselves around copper very readily. What this does is creates another reversible reaction that is present in solution. So this copper plus the 4 ammonias is known to be able to give us the complex ion that I have listed here. So we have a copper, and these brackets are not concentration of, this is just like an outer set of parentheses. So in fact, just for clarity's sake, I'll just make these another set of parentheses here. So we're not looking at specifically a concentration of, but here we are looking at a polyatomic ion where we have a copper in the center surrounded by 4 ammonia. There's a 2+ charge on it. This reaction, creating the complex ion, is also reversible in solution. It is not going to be a straightforward like precipitation reaction. Because the ammonias are only held on the copper by intermolecular forces, if we increase the temperature enough or increase the energy in solution enough through like stirring, we can knock a couple of the ammonias off. So this is definitely a reversible reaction situation. But if we add ammonia in the first place, we are going to be decreasing the copper concentration in the first reaction. What this means is that we are going to have to shift from reactant to product to accommodate the loss of the copper. We're going to have to create more product in order to replace the copper that is lost when forming this complex ion with ammonia. So here's how we can see that the complex ion formation from a metal ion that is dissolved in solution is always going to increase the solubility of the solid that you started with. Because when we make a complex ion, we're always going to be pulling some of the ion away from the original dissolution reaction. Now, what's really cool about this type of problem, this type of equilibrium, because we have 2 reversible reactions linked together inherently, now we can also change or shift the nature of our first reaction by shifting something according to Le Chatelier's principle in the second reaction. So adding stress to either one of these reactions now is going to inherently affect the other. We're not going to work through any of those types of problems quantitatively, but suffice to say that since we have another equilibrium expression here, we can write another type of equilibrium constant for this expression. Now, this type of equilibrium constant, just like how the solubility of our mostly insoluble stuff has a special equilibrium constant known as KSP, the formation of a complex ion also has a special equilibrium constant known as KF, K of formation. Now, for this type of expression, we're going to write out, or for this type of reversible reaction, we're going to write out the expression in the exact same way, again, that we have before. It's always product divided by reactant. And in this case, all of our products and reactants are aqueous. So the equilibrium expression here would be concentration of the CuNH3, 4, 2+, all divided by the concentration of our copper ion, Cu2+, and the concentration of our ammonia, and that's going to be raised to the 4th since we have a 4 in front of the ammonia. Now, are we going to be doing anything quantitatively with this KF? Probably not, but I still wanted to introduce the concept of the KF just because it is also laid out in the textbook. I don't want there to be any type of confusion because I haven't addressed something that's in the textbook for anyone who is like adamantly reading along at this point because we are all at long distance. But if we were to work through some type of KF problem, it would not be in this larger context tying these 2 reversible reactions together. That math just gets really messy really fast. So when it like moving forward when it comes to these types of problems, we're always only ever going to be looking at one equilibrium context at a time when we're actually quantitatively working through the problems. Qualitatively, we can stack together as many reversible reactions as we want and use Le Chatelier's principle to predict the direction of the reactions if we add a stress to one, which will have an effect on another, which will have an effect on another. That's pretty easy to predict. Quantitative stuff gets very messy. So this is going to be where we then conclude our conversation on solubility for now. But we do have a way then now, looking back to, without having to memorize any certain set of rules, we have a way to predict whether or not a solid is going to dissolve in solution, whether a precipitate will form if we've mixed two solutions together. We know exactly how much of that solid is going to dissolve into solution, like what the solubility actually is, and we also have the means to predict, based on changing other factors, other stressors, how the solubility of that solid is going to be affected. And that is going to be it for the day. So, as always, if you would like some extra practice, here are some practice problems, suggested section review problems pertaining to Le Chatelier's principle and solubility. There's only a couple here, so some extra practice will be coming in the form of homework. As always, though, if you have any questions, please do not hesitate to reach out and ask those questions. And until next time, class is dismissed.